Imagine a tiny world lost in the dark between Saturn and Uranus, where the rules of physics don't apply, a place where rings form where moons should be, and ancient gases leak from a dying heart. We've just discovered it's not a frozen relic. It's a live broadcast of a cosmic crime scene, and we are the first witnesses. The greatest mysteries are not always the ones that arrive with fanfare from the great dark between the stars. Sometimes they are the ones that have been with us all along, hiding in the familiar spaces of our own cosmic neighbourhood, waiting for us to look at them with new eyes and finally see the impossible staring back at us. While the world of astronomy has been rightly captivated by the fleeting visits of interstellar objects like 3E Atlas, heralding them as the most exotic and alien visitors we have ever studied, a far stranger and more profound drama is unfolding in the cold, silent depths much closer to home. If the enigma of Chiron has captured your imagination the way it has gripped the entire field of planetary science, go ahead and hit that like button and subscribe to the channel. You will not want to miss the moment the next observation turns everything we think we know on its head. I'm always fascinated to see where our community is watching from, so leave a comment down below. Tell me what part of the world you're in and what time it is for you right now. 18 astronomical units from the Sun, in the gravitational badlands between the orbits of Saturn and Uranus. The true outlier of our solar system is not a visitor at all. It is a permanent resident, an ancient traveller that has been on a billion-year journey through our system, and we are only now realising that it is perhaps the most bizarre object we have ever discovered. Its name is 2060 Chiron, and it defies every comfortable category we have ever invented. It is a comet that should not be active, an asteroid that breathes, a tiny world encircled by rings that, according to every fundamental law of orbital mechanics we hold dear, should not exist. These are not just simple bands of debris, they are structured, organised, and confined rings, a miniature Saturn orbiting a body barely 220 kilometres across. Even more baffling is their location. They exist in a gravitational zone where the physics of tides and attraction dictate that they should have collapsed under their own gravity and coalesced into a moon millions of years ago. Yet there they are, pristine and persistent, a cosmic contradiction spinning in the void. And adding another layer of profound mystery, Chiron is not a frozen, static relic. It is alive with activity, venting primordial gases, methane, propane, and others, into the vacuum, a slow exhalation of materials that should have been locked away in its deep freeze for eons. It is a time capsule cracked open, showing us a chemistry of the solar system's infancy that we thought was lost to time. Stay with me on this journey, because what we are witnessing around this tiny distant world is not just a static picture of the past. It might be a live broadcast of the birth of a moon, a process we thought took millions of years, unfolding on a human timescale right before our eyes, challenging our very understanding of how planetary systems are built. To understand why Chiron is such a bombshell, we must first look at what we thought we knew. The past few years have felt like a golden age of interstellar discovery. When 2I Borisov swept through our system in 2019, it was a historic moment, proof positive that we could indeed catch objects from other star systems on their fleeting passage through our own. Then, with the arrival of 3E Atlas in 2025, the excitement reached a fever pitch. Here was another traveller from the void, carrying with it the untold stories and exotic chemistries of a star system far from our own. The headlines were deservedly dramatic, speaking of alien ices and chemistry that had never felt the warmth of our sun. It was easy to get swept up in the hunt for the next great interstellar interloper, to believe that the most profound secrets lay out there, in the great beyond. But this focus on the distant and the foreign caused us to overlook the anomaly that was right under our noses all along. The weirdest object in our solar system isn't a visitor, it's a local. We've known about it since 1977, when astronomer Charles Cowell spotted it from the Palomar Observatory. It was catalogued, classified, and, we thought, understood. But Chiron was quietly harbouring secrets that would only reveal themselves decades later. Secrets that make those interstellar comets look almost mundane by comparison. Chiron exists in a category of its own, a celestial centaur. In mythology, centaurs were hybrid creatures, half human, half horse. In astronomy, centaurs are hybrid objects, caught between the worlds of asteroids and comets, orbiting chaotically in the space between Jupiter and Neptune. They are thought to be refugees from the Kuiper Belt, the distant ring of icy bodies beyond Neptune, which were kicked inward by gravitational encounters with the giant planets, sent on a wandering path that will inevitably end in their ejection from the solar system or their destruction as they fall sunward. They are objects in transition, and Chiron is the most transitional of them all. For decades, its story seemed straightforward. First, it was an asteroid. Then, as telescopes improved, astronomers noticed it occasionally developed a coma, the fuzzy envelope of gas and dust that characterizes active comets. So, it was reclassified. It was a comet after all, just one with an unusually large orbit. Case closed. We could move on. But Chiron refused to let us move on. It began to behave in ways that defied this simple classification. The first major clue that something deeply strange was happening around Chiron came in 2011 from one of astronomy's most powerful and elegant techniques, the stellar occultation. This is a celestial alignment where a distant object, in this case Chiron, passes directly in front of a star. By carefully measuring how the star's light dims and flickers as the object blocks it, astronomers can infer incredible details about the object's size, shape, atmosphere, and whether it has any companions like moons or rings. On that day in 2011, as Chiron passed in front of the star, the light did not simply blink out once as its solid body crossed the line of sight. It flickered multiple times, and the flickers were symmetrical, happening on both sides of the central occultation. It was as if something with structure, something organized, was surrounding Chiron and blocking the starlight in a precise repeating pattern. The data was puzzling, but the scientific community is conservative by nature. The initial interpretation leaned toward the known. Perhaps these were jets of gas and dust, the kind of messy, transient features you would expect from an active comet. Perhaps it was a shell of debris, recently ejected and soon to dissipate. The idea of permanent, stable rings around a tiny active comet seemed too far-fetched, too implausible. So the mystery was filed away, a curiosity to be revisited with better data. But Chiron was not done. It had more to show us. The years passed, and with each new observation, the puzzle only grew more complex. In 2022, another occultation provided another cryptic dataset. Then, on September 10th, 2023, everything changed. A major, internationally coordinated occultation campaign, led by teams at the Instituto de Astrofísica de Andalucía, captured the event with unprecedented precision. Multiple telescopes across different locations tracked the shadow of Chiron, giving astronomers not just a single slice of data, but a multi-dimensional view of whatever was surrounding this enigmatic body. The results, published in the Astrophysical Journal, were stunningly unambiguous. The flickers were not jets. They were not temporary shells. They were rings. At least 3 distinct, narrow and incredibly well-defined rings at distances of approximately 273, 325 and 438 kilometers from Chiron's center. And beyond them, a fainter, more diffuse feature stretched out to a staggering 1,380 kilometers. The realization was profound. Chiron, this small cometary centaur, possessed a complex ring system. This discovery alone was enough to shatter paradigms. Ring systems were the domain of giant planets, the majestic bands of Saturn, the faint loops of Jupiter and Uranus. These are features of massive worlds whose immense gravity can shape and control vast swarms of orbiting debris. A few other small bodies, like the centaur Chariklo and the dwarf planet Haumea, were known to have rings, but these were simpler, often explained as the recent aftermath of a catastrophic collision, a temporary debris field that would eventually either fall back or dissipate. Chiron's rings were different. They were multiple. They were structured. They were confined into sharp, narrow bands, implying a stability and organization that screamed of a system that had been there for a long, long time. But the most shocking detail, the one that truly broke our models, was the location of the outermost ring. It sat far outside Chiron's Roche limit. The Roche limit is not just another equation in an astrophysics textbook. It is a fundamental line in the sand drawn by gravity itself. Formulated by the French astronomer Édouard Roche in the 19th century, it defines a critical distance from a celestial body inside which the tidal forces, the difference in gravitational pull between the near and far sides of an object, overcome the self-gravity that holds that object together. Imagine a small moon orbiting a planet. The side of the moon facing the planet is pulled more strongly than the side facing away. Inside the Roche limit, this difference is so severe that the moon cannot hold itself together. It is stretched and torn apart, its debris spreading out to form a ring. This is why Saturn has glorious rings instead of a large moon orbiting in that same space. Any moon that ventured too close would be shredded. Conversely, outside the Roche limit, tidal forces are weaker and self-gravity wins. Debris particles can gently collide, stick together, and over time accrete into larger and larger bodies, eventually forming a cohesive moon. This is the simple, elegant, and universally accepted rule. Inside the Roche limit, rings. Outside the Roche limit, moons. Now, apply this to Chiron. With a radius of about 110 kilometers, its Roche limit is calculated to be somewhere between 200 and 300 kilometers from its center. The problem is immediately and glaringly obvious. The ring at 438 kilometers and the faint feature at 1,380 kilometers are far, far outside this boundary. According to every textbook, this material should not be in the form of a ring. For millions of years, the particles in these rings should have been gently colliding, aggregating and snowballing into one or more small moons orbiting Chiron. The fact that they haven't, the fact that they remain in this pristine disk-like state, is a direct violation of classical orbital mechanics. It is as if you dropped a handful of marbles and they refused to fall to the floor, instead hanging in mid-air in a perfect organised pattern. The rings of Chiron are not just an interesting feature, they're a profound anomaly, a challenge to our most basic understanding of how matter behaves in space. The data that revealed this violation came from a series of painstaking observations, a global effort to read the braille of flickering starlight. The occultation of December 15, 2022, was a pivotal moment. Teams of astronomers across several continents positioned their telescopes along the narrow path on Earth where Chiron's shadow would fall. They were ready to capture the brief blink of the background star. What they recorded was anything but a simple blink. The starlight dimmed in a complex multi-stage pattern. There was a broad, extended dimming, suggesting a diffuse cloud or disk stretching out to about 580 kilometers from Chiron, much larger than the solid body itself. And superimposed on this broad shadow were sharp, narrow dips in the light curve. These were the rings, revealing themselves as dense, confined concentrations of material. The initial analysis was cautious, as all good science should be. Perhaps these were just particularly dense regions within a larger, chaotic debris disk. Perhaps they were temporary structures, like the jets of comets, that just happened to be aligned in a ring-like pattern at that moment. But the geometry was too perfect. The sharpness of the dips indicated structures that were razor-thin, not fluffy, transient clouds. And when the team calculated the distances, the inescapable conclusion emerged. At least one of these sharp features was orbiting well beyond the calculated Roche limit. Material that should have been busy forming a moon was, against all odds, still a ring. The September 10, 2023, occultation removed all remaining doubt. This was a multi-chord event, meaning the shadow was observed from multiple, widely separated locations. This allowed astronomers to triangulate, to build not just a one-dimensional slice, but a two-dimensional map of the ring system. The results were breathtaking in their clarity. 3 distinct rings, all orbiting in the same plane, a coherent, organised system tilted relative to Chiron's own orbit around the Sun. The pole of this miniature ring system was precisely calculated. This was not a random collection of junk. This was a settled, stable architecture. And then there was that enigmatic, faint outer feature at 380 kilometers, a ghostly halo whose nature remains one of the most tantalizing puzzles. But occultations, for all their power, only tell us where the material is. They don't tell us what it is made of or what is driving the incredible activity on Chiron itself. For that, we needed to turn a different kind of eye toward this distant world, an eye that could see not just in light and shadow, but in the chemical fingerprints of molecules. We needed the James Webb Space Telescope. In July of 2023, JWST trained its formidable near-infrared spectrograph, NIRSpec, on Chiron. For hours, it collected the faint light, breaking it down into a spectrum that revealed the precise chemical composition of Chiron's surface and its surrounding coma. What it found was a world far more complex and primitive than anyone had imagined. The surface was a menagerie of ices. There was water ice, but mostly in an amorphous, disordered state, a key clue we will return to. There was carbon dioxide ice and carbon monoxide ice, and then the plot thickened. JWST clearly detected the spectral signatures of ethane, propane, and acetylene. These are simple organic molecules, the kind of building blocks that are thought to have been abundant in the early solar system. On most comets, these volatiles are locked away deep in the interior, protected within a matrix of water ice. On Chiron, they were right there on the surface, exposed and active. The biggest surprise, however, was methane. JWST didn't just find methane ice. It found methane gas in a state of non-local thermal equilibrium, fluorescing under the feeble sunlight. This was the smoking gun. Methane was actively and vigorously being outgassed from Chiron's interior, venting into space and creating the coma that gives it its cometary identity. In a follow-up observation in January 2024, as part of JWST's second cycle of observations, the telescope went back for a closer look, this time to measure the rate of this outgassing and to map its source. The numbers were staggering. Chiron was releasing approximately 1.6 skex in 10^-27 molecules of methane every second. For a body of its size, this is an enormous, almost violent level of activity. The carbon dioxide production was lower but still significant. Intriguingly, the mapping showed that the methane and carbon dioxide were not coming from the same places. They were venting from different regions on the surface, suggesting a complex heterogeneous interior where different volatiles are stored in different reservoirs and released under different conditions. And in another twist that confounded model predictions, carbon monoxide gas, which should have been a major component of the outgassing, was conspicuously absent, not detected above the noise level of the instruments. Put it all together, the rings where moons should be, the complex surface chemistry, the vigorous and localized outgassing of primordial gases, and you have an object that simply cannot be explained by our existing categories. Chiron is not a comet with rings, it is not an asteroid with a coma, it is a hybrid system, a planetary embryo frozen in time, or perhaps a planetary embryo that is just now awakening. It is a natural laboratory where the rules of small body physics are not just being observed, but are being written and rewritten before our very eyes. To grasp the full strangeness of Chiron, we must journey to its home, to the deep freeze of the outer solar system where it conducts its impossible ballet. Chiron's orbit carries it between 8 and 19 astronomical units from the Sun, but it spends most of its time in the profound cold around 18 AU. To contextualize this, Earth basks at 1 AU, Jupiter orbits at 5 AU, Saturn at 9.5. Chiron lives in the darkness far beyond Saturn, where the Sun is a mere bright star in a black sky, its light feeble and its warmth almost non-existent. Here, temperatures hover between 80 and 100 Kelvin, a bone-shattering 190 to 170 degrees Celsius. At these temperatures, chemistry almost grinds to a halt. Nitrogen, the gas that makes up most of our air, is a solid ice. Methane, the main component of natural gas, is not a vapor but a frozen solid. This is a realm of deep freeze where everything should be locked in a perpetual unchanging stasis, a fossil preserved from the dawn of the solar system. And yet, Chiron is active. It has a coma, it vents gas continuously, it behaves for all the world like a comet, but it is doing so in an environment where classic cometary activity is utterly impossible. The energy from the Sun at that distance is simply too weak to heat the surface enough to sublimate ices directly from solid to gas. So what is the engine? What force is driving this activity in the absolute cold and dark? The leading hypothesis is as elegant as it is powerful, and it centres on a fascinating property of water ice itself. Water ice is not always the same. We are most familiar with crystalline ice, where the water molecules are arranged in a neat, orderly hexagonal lattice. This is the ice in your freezer, in glaciers, and in snowflakes. But there is another state, amorphous ice. In this form, the molecules are frozen in place in a chaotic, disordered, glass-like state, much like the structure of window glass. Amorphous ice does not form under everyday conditions on Earth. It requires extremely cold temperatures and rapid condensation, exactly the conditions present in the outer reaches of the solar nebula or in the interstellar medium. For billions of years, Chiron's water ice has likely existed in this amorphous metastable state, And herein lies the key. Amorphous ice is not stable. It harbours a latent energy, a driving force to transition to the more stable crystalline form. When this phase change occurs, it is not a gentle process. It is an exothermic transformation, meaning it releases heat, a significant amount of it. This is not just a theoretical concept. It is a measurable physical process that can release enough energy to significantly warm the surrounding material. But the amorphous ice engine has another, even more critical feature. Its disordered, porous structure is a perfect trap for other, more volatile molecules. Gases like methane, carbon monoxide, and carbon dioxide can become physically imprisoned within the frozen water matrix, adsorbed onto the surfaces of countless microscopic pores, unable to escape. They are held in a frozen prison. The trigger for this entire sequence is temperature. The amorphous to crystalline phase transition for water ice kicks into gear at around 61 Kelvin. Chiron's surface temperature, hovering between 80 and 100 Kelvin, is precariously perched right above this threshold. It doesn't take much, a slight nudge in temperature, from the subtle changes in solar heating as Chiron moves along its slightly eccentric orbit, or from the changing angles of its seasons, could be enough to push patches of the surface ice past the 61 Kelvin mark. When that happens, it's like pulling the pin on a grenade. The amorphous ice begins to crystallize. The process releases heat which warms the adjacent ice, causing the crystallization front to propagate inward, a wave of transformation moving through the body. As it crystallizes, the ice matrix changes structure, and the trapped volatile gases are suddenly released. They flash from solid to gas in an instant, and with nowhere to go, the pressure builds dramatically. This pressurized gas seeks escape, fracturing the overlying ice, blasting through the crust, and venting into space in powerful jets. This process is a game changer because it is internally driven. It does not rely on direct solar heating. It uses solar energy only as a minor trigger. The real power comes from the latent energy stored in the ice itself during its formation billions of years ago. Chiron is quite literally powering its own activity by unleashing the fossil energy locked in its own structure since the day it was born. This hypothesis provides a beautifully coherent framework for explaining not just the activity, but the rings themselves. Remember the significant brightness outburst Chiron experienced between March and September of 2021? Its brightness jumped by 0.6 magnitudes, a telltale sign of a massive ejection of dust and gas. If such an outburst was driven by a major amorphous ice crystallization event, it would have vented an enormous volume of material into space. Now consider the physics of that ejection. If the material is blasted off with a certain range of velocities, some of it will simply escape Chiron's weak gravity, drifting away into interplanetary space. But some of it, launched with just the right speed and direction, would achieve orbit. It would become a new supply of ring material, a fresh infusion of particles to replenish the rings, replacing what is inevitably lost over time through collisions or gravitational perturbations. This transforms our understanding of the ring system from a static relic to a dynamic living structure. Chiron's rings may not be the ancient leftover of a single, cataclysmic collision. Instead, they could be a constantly renewed phenomenon, a persisting structure fed by a periodic engine deep within Chiron itself. The rings exist because Chiron is active, and its activity is driven by this slow-motion engine of phase change physics. It is a self-sustaining cycle, a feedback loop where the rings are both a product of and a witness to the ongoing geological life of this tiny world. But is this the whole story? The amorphous ice transition is a compelling protagonist, but in the complex theatre of planetary science, there are often other players on the stage. Could Chiron's activity be even more multifaceted? Could it be a multi-engine system? Consider cryovolcanism. We know that other icy worlds, like Saturn's moon Enceladus, possess geysers that erupt not from phase transitions, but from internal heat generated by tidal flexing or the decay of radioactive elements. Could Chiron, despite its small size, harbour pockets of residual heat from its violent past, heat that drives pockets of icy slush to the surface? Or consider mechanical fracturing. Chiron's rotation is known to be chaotic, a slow, unpredictable tumble through space. This constantly changing spin subjects its brittle crust to shifting stresses, which could open up cracks and faults over time. These cracks could tap into pressurized pockets of gas, creating vents and jets through a purely mechanical process, independent of any ice chemistry. And we cannot rule out impacts. The region Chiron inhabits is not empty. It is strewn with the leftover debris of solar system formation. A chance impact from a small meteoroid could excavate subsurface ice, vaporize it, and launch a plume of ejecta into orbit, providing another sporadic source of ring material. The truth is, Chiron is so complex and the data so rich with contradiction and surprise that it likely isn't a choice between one engine or another. The most probable and most exciting scenario is that all of these processes are happening simultaneously, in different regions, at different times. Amorphous ice may be crystallizing in one hemisphere, driving a steady plume of methane. A cryovolcanic vent, powered by some deep-seated warmth, could be spewing carbon dioxide in another. Meanwhile, the slow stresses of its tumbling rotation are steadily opening new fractures, and occasional impacts are kicking up local clouds of dust. This multi-engine model would perfectly explain the JWST data, showing different gases venting from different locations. It would account for the observed changes in the ring structure over time, as different outbursts from different sources inject material with different properties into the orbiting disk. Chiron, then, is not just an anomaly. It is a symphony of anomalous processes, a tiny world with a complex and vibrant inner life that we are only beginning to decode. It is a reminder that nature, when examined closely, rarely offers simple, single-answer solutions. It offers complexity, nuance, and a beautiful, confounding chaos that pushes us to think harder and see further. The violation of the Roche limit by Chiron's outer rings is not a minor discrepancy. It is a fundamental challenge to the physics we use to describe the architecture of every ringed system we have ever known. To appreciate the depth of this puzzle, we must delve deeper into the nature of gravity around irregular bodies and the dynamic forces that can, against all odds, create stability from chaos. The classical Roche limit calculation assumes a perfect spherical central body, but Chiron is anything but spherical. It is a traxial ellipsoid, a lumpy potato-shaped world whose gravity field is a complex and bumpy landscape, not a smooth, symmetrical well. This irregularity changes everything. The gravitational pull you feel orbiting Chiron is not the same in all directions. There are gravitational highs and lows, bumps and troughs created by its misshapen form. A particle orbiting Chiron does not travel a simple Keplerian ellipse. It dances through a constantly shifting potential field, its path perturbed by the peaks and valleys of gravity that rotate with the body itself. In 2025, a team of dynamicists led by researchers like Maddalena Morgado and Bruno Pereira published a groundbreaking study that modelled this very environment. They simulated the orbits of thousands of test particles around a digitally reconstructed triaxial Chiron, tracking their fates over decades of simulated time. The results were revelatory. The region close to Chiron, inside a boundary of about 260 kilometers, was a gravitational meat grinder. Orbits were wildly unstable, with particles either crashing into the surface within a few years or being flung out into the void of interplanetary space. This inner zone is a no man's land where nothing can persist. But beyond this chaotic inner boundary, something remarkable happened. The simulations revealed islands of stability, specific orbital distances where particles could survive for decades, centuries, or potentially much longer. These were not zones of perfect calm, but rather regions where the destabilizing tugs from Chiron's lumpy gravity were minimized or, in some cases, acted in a periodic stabilizing manner. The key to this stability appears to be spin-orbit resonances. As Chiron rotates, its asymmetrical gravitational field rotates with it. A particle orbiting at a certain distance will have a specific orbital period. If that orbital period is a simple integer ratio of Chiron's rotation period, say 1.3 or 1.5, the particle experiences the same gravitational tug from Chiron's bulges at the same point in its orbit every single time. This repeated rhythmic perturbation can actually confine the particle's orbit, preventing it from drifting inward or outward. It acts as an invisible shepherd, not a moon, but a gravitational waveform that herds particles into narrow bands. The simulation suggested that two of Chiron's rings, designated CH2R and CH3R, might be sitting precisely within these resonant stability zones. This provides a potential, and yet utterly fascinating explanation for how narrow rings can persist without the traditional shepherd moons we see around Saturn. Chiron's own rotation and irregular shape are creating a self-shepherding system, using the music of orbital resonances to conduct its rings into orderly bands. But this elegant solution also raises new and difficult questions. For one, resonances can be fragile. They require a certain level of dynamical calm to persist. The constant injection of new material from outgassing and the collisions between ring particles themselves should, in theory, disrupt these delicate resonances over time, causing the rings to spread and blur. So why haven't they? This is where the multi-engine model of Chiron's activity might come back into play. The very processes that threaten the rings might also be their salvation. The periodic outbursts that inject fresh material could also be resetting the system, pumping in new particles that quickly fall under the influence of the dominant resonances, maintaining the ring's density and sharp edges against the dissipative forces of collisions. It's a dynamic, pulsating equilibrium, not a static one. Another major question remains: where are the moons? Even with resonant confinement, the fact that the ring particles have not accreted into moonlets over millions of years is deeply puzzling. Outside the Roche limit, collisions between particles are thought to be sticky, low-velocity impacts that allow van der Waals forces or other weak bonds to glue particles together, starting the process of accretion. So why hasn't this happened around Chiron? One possibility is that the environment is just too violent. The constant jostling from resonant perturbations combined with the gentle but persistent pressure from outgassing gas might be keeping the particle swarm just stirred up enough to prevent the initial clumping from taking hold. It's like trying to build a sandcastle in a gently vibrating tray. The grains never get a chance to stick together properly. Another more speculative idea is that the ring particles themselves have unusual physical properties. Perhaps they are exceptionally fluffy, fractal-like aggregates with very low density, making them more prone to bouncing off each other rather than sticking. Or perhaps their surfaces are coated with a non-sticky material, like tholins, complex organic gunk that forms when simple ices are irradiated. The faint, diffuse outer feature at 1,380 kilometers adds another layer to the mystery. This is not a dense, narrow ring. It is a broad, tenuous cloud. Is it a failed ring, a region where resonances are too weak to confine material? Is it a debris field from a recently disrupted moonlet? Or is it the outermost reaches of an extended disk, where particles are so sparse that they rarely collide and are slowly being lost to space? We simply do not know. The Roche limit violation forces us to confront the fact that our physics, developed for the clean, massive systems of the giant planets, is insufficient for the messy, dynamic and small-scale reality of a world like Chiron. It shows us that gravity, when applied to irregular, active bodies, can produce phenomena we are only beginning to model, let alone understand. Chiron is teaching us that the universe of orbital dynamics is far richer and more inventive than our textbooks had allowed. One of the most revolutionary aspects of the Chiron system is that it is not a static snapshot of a past event. It is a living, breathing and evolving system, and we have the unprecedented ability to watch that evolution happen on a human timescale. In the grand, slow-moving theatre of planetary science, where processes typically unfold over millions or billions of years, this is akin to watching a flower bloom in time-lapse, rather than checking on it once a season. The evidence for this real-time change is etched into the observational record. The series of occultations from 2011, 2018, 2022, and 2023 do not all show an identical ring system. When astronomers compare these snapshots, they see subtle but significant differences. The density of the rings appears to shift. The relative brightness of one ring compared to another changes. The broad, diffuse disk inside the rings seems to expand and contract. There are hints of asymmetries, clumps or arcs of material that appear in one observation and are gone in the next. This is not the behaviour of an ancient settled system left over from a single collision eons ago. This is the behaviour of a dynamic, fluid environment, a system in a state of constant flux. Then there was the great outburst of 2021. For several months, Chiron's overall brightness increased by 0.6 magnitudes. From our vantage point on Earth, this was a clear and dramatic signal that something major had happened on or around Chiron. a 0.6 magnitude jump is not a small fluctuation. It represents a significant ejection of material, enough to dramatically increase the total reflective surface area of the dust and gas cloud surrounding the nucleus. This was a planetary scale event. If the amorphous ice engine is correct, this could have been a major crystallization event, perhaps triggered by a seasonal temperature change or the collapse of a subsurface cavity that released a colossal volume of trapped gas and carried countless tons of dust with it into space. This single event may have injected more fresh material into the ring system than is typically lost over decades. It was a moment of renewal, a demonstration that Chiron's rings are not a finite resource but a renewable one, fed by the internal dynamics of the body itself. This leads to the most thrilling and profound question we can ask about Chiron. Are we watching a moon being born? Consider the process. Chiron vents material. This material, if it has the right velocity, enters orbit. Initially, it forms a disk or a ring. Within that disk, particles collide. Most collisions are gentle. In the cold of space, especially with ices, these gentle collisions can lead to particles sticking together, a process known as accretion. Over time, these initial aggregates grow, sweeping up more and more material in their path, becoming planetesimals, then moonlets. This is the very process by which planets formed around the Sun, and moons formed around the giant planets. We have always assumed it was a process that took millions of years, far too slow for any human, or even any human civilization to witness. But what if, in the unique environment around Chiron, it is happening faster? The constant resupply of fresh, fine-grained material from outgassing could be dramatically accelerating the initial stages of accretion. The ring system might be a nursery, and we might be seeing the first tiny kilometre-sized moonlets beginning to form within the densest parts of the rings. Our current telescopes cannot resolve such small objects at that distance, but future occultations might reveal their presence through telltale dips in starlight that move independently of the rings. Or perhaps we are seeing the opposite. Maybe the rings are a transient, ephemeral phenomenon. Perhaps Chiron goes through active phases, driven by its internal engines where it vigorously vents and maintains a glorious ring system for a few centuries or millennia. Then, when the volatile reservoirs in its outer layers are temporarily depleted, the outgassing stops. Without this constant replenishment, the rings would quickly succumb to their own dynamics. Collisions would grind the particles down to dust, gravitational perturbations from the Sun would slowly disperse the material, and the rings would fade away, either falling back onto Chiron's surface or drifting off into space. In this scenario, we are not witnessing the birth of a moon, but the brilliant final flowering of a ring system during a particularly active period in Chiron's long life. The incredible fortune is that we are here to see it at all. We just happen to be living in the cosmic moment when this tiny distant world has decided to put on its most spectacular show. This is the core of Chiron's scientific value. It is a natural laboratory. We can propose a model, for example, that resonant shepherding maintains the rings, and then we can test it. We can predict that if this model is correct, the rings should maintain their narrow structure over the next decade. Then we can wait and watch and see if they do. We can look for the predicted moonlets. We can monitor the outgassing rates and see if they correlate with changes in ring density. This is the scientific method in its purest form, applied to a planetary scale experiment. No other object in the solar system offers this combination of accessibility, complexity, and rapid evolution. Mars changes over eons. Jupiter's storms change over years. Chiron's rings and activity could change over months. A single graduate student could write their entire PhD thesis on the changes observed in Chiron over their time in graduate school. That is an astonishing thought. It makes Chiron not just a subject of study, but a partner in a dialogue. We ask a question with our models, and Chiron provides an answer with its behaviour. It is a conversation across 18 astronomical units of space, a conversation that is reshaping our understanding of how small worlds live, breathe, and build their own miniature cosmic families. The amorphous ice hypothesis is a powerful and elegant explanation for much of what we see at Chiron. It provides a clean, single-engine model that can account for the outgassing, the outbursts, and the replenishment of the rings. But science, at its best, is inherently uncomfortable with answers that are too clean. Nature is messy, complex, and redundant. It rarely puts all its eggs in one basket. So, we must ask the uncomfortable question: who says Chiron has only one engine? What if the reality is even more bizarre, with multiple independent processes working in concert or in competition to create the chaotic, vibrant system we observe? Let's seriously consider the other potential engines. First, cryovolcanism. We have direct, stunning evidence of this on Saturn's moon Enceladus. There, towering geysers of water ice and vapour erupt from tiger-stripe fractures near its south pole, powered not by phase transitions, but by the heat generated from the tidal flexing of its interior as it orbits Saturn. This heat maintains a global subsurface ocean, which periodically erupts into space. Chiron is not tidally flexed by a giant planet, but it is an ancient body that has been wandering the solar system for billions of years. It could contain long-lived radioactive isotopes like potassium-40, thorium-232 or uranium-238. The decay of these elements generates heat, and in a small, poorly conductive body, that heat can build up, creating localized hotspots. These hotspots could slowly melt the icy interior, creating pockets of liquid water or briny sludge, laced with ammonia or salts that act as anti-freeze. When the pressure in these subsurface reservoirs becomes too great, they could rupture the surface, creating cryovolcanic vents that spew this material into space. This would be a source of activity completely independent of the amorphous ice transition, potentially releasing different ratios of volatiles and dust. Then there is mechanical fracturing. Chiron's chaotic rotation is a critical piece of this puzzle. A body that tumbles irregularly is subject to constantly changing thermal and gravitational stresses. Its surface is repeatedly stretched and compressed. Over time, this can lead to fatigue and the formation of deep global fracture systems. These fractures could act as ready-made pipelines to the interior. If they tap into a pressurized reservoir of gas, whether from crystallizing amorphous ice or from a cryovolcanic chamber, they would provide an instantaneous conduit for that gas to escape. This process could explain sudden, localized jets that appear and disappear as different fractures are opened and closed by the changing rotational stresses. And we must not forget impact gardening. The region of space Chiron inhabits is not empty. It is populated by countless other small centaurs and Kuiper Belt objects, and a hail of smaller debris. An impact, even from an object a few meters across, would be a violent energetic event on Chiron's surface. The kinetic energy of the impact would instantly vaporize a significant amount of ice at the point of collision. This would create a transient, explosive jet of gas and dust, launching material with a wide range of velocities. Some of this ejecta would certainly achieve orbit, contributing to the rings. An impact could also trigger wider scale changes, such as causing landslides that expose fresh, volatile-rich ice, or even triggering larger-scale crystallization events by sending shockwaves through the crust. Now imagine all of these engines running at once. In one region of Chiron, a patch of amorphous ice is crystallizing, releasing a steady, diffuse plume of methane-rich gas. In another, a cryovolcanic vent powered by radioactive decay periodically erupts, sending fountains of water ice and carbon dioxide into the sky. Across the surface, the slow grind of its tumbling rotation is steadily opening new fractures, which suddenly release puffs of gas when they connect to a pressurized pocket. And every few years, a random impact creates a brilliant short-lived flash and a cloud of ejecta. This multi-engine model is no longer a neat single-equation problem. It is a complex, coupled system with multiple feedback loops. An outburst from one engine could alter the surface, triggering activity in another. A major impact could reset the local thermal structure, changing the rate of crystallization for centuries. This complexity is both the frustration and the glory of Chiron. It is frustrating because it means we cannot write a simple, predictive model of its behavior. We cannot say with certainty what Chiron will do in 10 years, but it is glorious because it means Chiron is a truly living world, with a rich and varied geological life. It is not a simpleton, it is a genius of complexity, showing us just how dynamic and inventive a small ball of ice and rock can be. This model also provides the most coherent explanation for the JWST data. The fact that methane and carbon dioxide are venting from different locations is a direct prediction of a multi-engine system. Different processes tap into different volatile reservoirs. The amorphous ice might be particularly good at releasing trapped methane, while cryovolcanic processes might be better at mobilizing carbon dioxide from deeper, warmer regions. The absence of expected carbon monoxide could be explained if the particular engine that was most active during the JWST observation simply doesn't access the CO reservoir. Chiron, therefore, is not an object we will ever fully solve. It is an object we will continue to learn from. Each new observation reveals another layer of its complexity, another piece of its internal machinery. It teaches us humility, showing us that our desire for simple, clean answers is often a poor match for the inventive, messy, and wonderfully complicated reality of the cosmos. The enduring mystery of Chiron's narrow rings brings us to one of the most persistent questions in all of ring science. What is confining them? In every other known case, narrow planetary rings are not self-confining. They are the product of shepherding. The magnificent razor-sharp edges of Saturn's rings, the braided F ring, the eccentric arcs of Uranus, all of these are sculpted and maintained by the gravitational influence of small moons. These shepherd moons, some only a few kilometers across, orbit just inside or outside the ring material. Their gravity exerts a constant periodic tug on the ring particles, preventing them from drifting out of their designated lane. It is a form of cosmic traffic control, and it is incredibly effective. So, when we discovered that Chiron had multiple narrow rings, the immediate instinctive question from every planetary scientist was, where are the shepherds? We have looked. Through direct imaging and through the painstaking analysis of occultation data, astronomers have searched for the telltale signs of these tiny moons. Thus far, they have found none. This is a major problem. Without a confining mechanism, narrow rings should spread out due to collisions and gravitational interactions between the particles themselves. They should blur into a featureless broad disk within an astronomically short period, perhaps just thousands of years. The fact that Chiron's rings are sharp and well-defined means something must be actively confining them right now. The absence of detected shepherds has forced us to consider radical alternatives. The first and simplest is that the shepherds are there, but we just can't see them. They could be very small, only a few hundred meters across, and very dark with a low albedo that makes them reflect almost no sunlight. Embedded within the bright rings, such a dark, tiny object would be like a single black pebble in a blizzard, virtually impossible to pick out with current telescopes. This remains a very real possibility. But the more intriguing possibility is that Chiron doesn't need shepherds at all. This is where the groundbreaking dynamical simulations come back into play. The 2025 study that revealed the islands of orbital stability, driven by spin-orbit resonances, also suggested a mechanism for self-shepherding. If the rings are indeed sitting in these resonant zones, then Chiron's own lumpy gravity is acting as the shepherd. The resonances create locations where particles' orbits are stable, and just outside these locations the orbits are unstable. This creates a virtual barrier, an invisible wall that particles cannot cross. It's as if the ring is orbiting inside a gravitational corral, whose fences are made not of matter, but of mathematical relationships between Chiron's rotation and the particle's orbit. This would be a completely new type of ring confinement mechanism, one never before observed in the solar system. It would mean that small, irregular bodies can maintain complex ring structures through their own intrinsic properties, without the need for a retinue of satellites. This has profound implications. It suggests that ring systems could be much more common around small bodies than we ever thought, because they wouldn't require the specific conditions needed to form and retain shepherd moons. There is a third hybrid possibility that involves Chiron's activity. The constant outgassing itself could play a role in confinement. When gas is vented from the surface, it doesn't just disappear. It forms a tenuous temporary atmosphere around Chiron. This gas exerts a drag force on the dust particles in the rings. This drag is minuscule, but over time it can cause particles to lose energy and drift inward. However, if the outgassing is not uniform, if it comes from specific active regions on the surface, it could create an asymmetric drag force that preferentially removes particles from certain orbital zones and not others. Over time, this could help sharpen the edges of rings or even create gaps. It's a subtle effect, but in the delicate balance of forces around a small body, it could be significant. So, we are left with three competing and not mutually exclusive hypotheses for the ring's confinement. 1. Undetected, traditional shepherd moonlets. 2. Self-shepherding via gravitational resonances with Chiron's irregular shape. 3. Gas drag confinement from asymmetric outgassing. The path to distinguishing between these is clear but immensely challenging. We need higher resolution observations. A future, powerful space telescope might be able to directly image a shepherd moonlet if one exists. More multi-chord occultations with even greater precision could map the ring edges with enough detail to see if they align perfectly with predicted resonance locations, or if they show kinks and waves that are the hallmark of a nearby shepherd's gravity. The ultimate test would be a dedicated spacecraft mission. A probe flying past Chiron could use its cameras to resolve the rings directly, looking for embedded moonlets and mapping the fine structure of the rings. It could use radio science to map Chiron's gravitational field in exquisite detail, confirming the exact locations of the resonances. Until then, the shepherd moonlet hypothesis remains in a state of suspended animation. Not proven, but far from dead. It's a testament to the depth of the mystery that after years of intense study, we still cannot answer the most basic question about Chiron's rings. What is holding them together? This is not a failure of science. It is the engine of science. It is the unanswered question that drives the next observation, the next simulation, the next great leap in understanding. Chiron is holding its secrets close, and in doing so, it is forcing us to become better detectives. To truly appreciate Chiron, we must pull back from the close-up view of its rings and jets and see it in its proper context, as a traveller on an epic journey, a piece of cosmic history that is revealing the hidden dynamics of our solar system. Chiron is an exile. It was not born in its current unstable orbit between Saturn and Uranus. That region is a gravitational shooting gallery. No object can form there and expect to survive for long. Chiron is an immigrant. It almost certainly originated in the Kuiper Belt, the vast cold repository of primordial icy bodies beyond the orbit of Neptune. For billions of years, it was a quiet citizen of this distant realm, a frozen fossil from the solar system's birth. But then, a gravitational encounter with Neptune, or perhaps with another large Kuiper Belt object, perturbed its orbit. It was kicked inward, beginning a long, chaotic migration into the realm of the giant planets. It became a centaur, an object on a doomed path. Its current orbit is transient, with a dynamical lifetime of only about 1 million years, a mere blink in cosmic time. Eventually it will have another close encounter with a giant planet, most likely Jupiter. That encounter will be its final act. It will either be flung out of the solar system entirely, becoming a lone wanderer in interstellar space, or it will be sent plunging sunward, where it will become a short-period comet, destined to vaporize itself in a series of fiery passes close to the Sun. But right now, in this brief window, it is in a transitional state. It is not a pristine Kuiper Belt object anymore. The journey inward has warmed it, activated it, and transformed it. But it is not yet a full-blown, sun-grazing comet. It is caught in between, and this in-between state is a scientific goldmine. It allows us to study the process of cometary activation as it happens. We can see what happens when a primordial ice ball is taken from the deep freeze of the Kuiper Belt and placed in a slightly warmer environment. We can watch its ices begin to sublimate, its crust fracture, its internal structure reorganize. Chiron is showing us the missing link between the dormant builders of the outer solar system and the spectacular, self-destructive comets of the inner system. This raises a critical question. Is Chiron unique, or is it representative? Are there hundreds of other centaurs out there right now with similar ring systems and complex activity that we simply haven't detected yet? The known centaurs number only in the hundreds, but this is believed to be a tiny fraction of the total population. Most are too faint and too distant for our surveys, and detecting rings requires the precise alignment of a stellar occultation, which is a rare and observationally challenging event. The fact that we have already found rings around Chiron, Chariklo and Haumea suggests that rings on small bodies are not freak occurrences. They might be a common, if temporary, phase in the life of a migrating icy body. Perhaps when a Kuiper Belt object is first kicked inward and begins to warm, the onset of activity naturally lofts material into orbit, creating a ring system. This ring system might then be a nursery for moon formation. If the object remains stable for long enough, the rings could coalesce into one or more moons. We see this with the dwarf planet Orcus, which has a large moon, Vanth, and with Pluto and its system of 5 moons. Perhaps these are the end result of the process we're seeing in its early stages at Chiron. Or, if the object's journey is too chaotic, the rings are simply lost, dissipated before they can form a moon. In this grander view, Chiron is not an oddity. It is a snapshot of a universal process. It is showing us that the early solar system, during the era of planet migration and the late heavy bombardment, must have been filled with such objects, countless small ringed bodies migrating inward, colliding, merging, and sometimes delivering their volatile rich material to the young inner planets. Chiron's specific chemistry is another chapter in this story. The presence of methane, ethane, and propane tells us that it formed in a very cold region of the nebula, likely the outer Kuiper belt or even the scattered disk, where temperatures were low enough for these supervolatiles to condense directly onto grains. These are the pristine ingredients of the solar system. When Chiron eventually meets its end as a Jupiter family comet, it will be delivering these primordial ingredients to the inner solar system. This is one of the key mechanisms by which Earth may have received its water and its organic compounds, the building blocks of life. So Chiron is more than just a curiosity. It is a window into the formation and evolution of our entire planetary system. It is a messenger from the distant cold reaches, telling us about the conditions of our birth and the dynamic processes that shaped our cosmic home. It is a living fossil, but unlike a dinosaur bone locked in rock, it is a fossil that is still moving, still changing, and still telling its story. By studying Chiron, we are reading a living history of the solar system, written in ice, gas, and dust. The story of Chiron, as presented so far, might seem like a straightforward march of discovery. Observations are made, models are proposed, and understanding grows, but the reality of science is far messier, more human, and more interesting. The study of Chiron is filled with controversies, competing interpretations, and healthy, vigorous debate. This is not a sign of weakness, it is the sound of a living, breathing scientific field. Not everyone in the planetary science community is fully convinced that Chiron has permanent, stable rings. The occultation data is compelling, but it is also indirect and subject to interpretation. You are trying to reconstruct a three-dimensional structure from a series of one-dimensional slices, the changes in starlight recorded at different locations on Earth. It is like trying to deduce the shape of a sculpture by only looking at its shadow from a few different angles. There is always ambiguity. Some researchers argue that what we are interpreting as rings could be something else, dense shell-like structures of debris from a recent massive outburst. A series of collimated jets that, by chance, were aligned in a ring-like pattern during the occultations, a temporary dust torus, a donut-shaped cloud, with denser regions that create the illusion of discrete rings. These are all legitimate alternative hypotheses. The problem is the sparseness of the data. While the 2023 occultation had multiple chords, it is still a limited dataset. To fully reconstruct the rings, you must interpolate between the data points and you must make assumptions, the biggest one being that the rings are symmetric and circular. What if they are not? What if the material is arranged in clumpy arcs like the rings of Neptune? If that were the case, it would completely change our interpretation of their stability and formation. Arcs are much harder to maintain than full rings and would point toward a recent violent origin or the presence of a specific confining resonance from a hidden moonlet. There is also a historical context to the skepticism. Before the 2011 occultation, the consensus was that Chiron was an active comet, and its variability was due to classic cometary jets. For researchers who spent decades working under that paradigm, the shift to a ringed world is a major conceptual leap. There is a natural and scientifically healthy conservatism that demands extraordinary evidence for extraordinary claims. Some of the older guard remain unconvinced, waiting for that one undeniable piece of evidence that rules out all other possibilities. There are also unpublished concerns and rumours within the community. Some astronomers point to asymmetries in the data that don't perfectly fit symmetric ring models. Others question the density and optical depth derived for the rings, suggesting they might be overestimated. The faint outer feature is a particular point of contention. Is it a real, physical structure, or is it an artifact of the data processing? The path forward through this controversy is the same as it always is in science: more and better data. We need more occultations. We need to observe Chiron passing in front of brighter stars, which would provide a clearer signal. We need to coordinate even larger campaigns with more telescopes to get a denser sampling of the shadow. We need spectroscopic studies of the rings themselves to determine their composition, which could tell us about their origin. And ultimately, we need a spacecraft. A direct image from a visiting probe would settle the debate instantly. Until then, the controversy will continue. Competing teams will publish papers supporting their interpretations. Conferences will feature lively, and sometimes heated debates. Peer reviewers will pick apart each other's assumptions. This is not a dysfunctional process, it is the process. It is how science self-corrects, how it slowly, painstakingly, moves toward a more accurate understanding of reality. The truth about Chiron's rings is not yet settled. It is emergent, and watching that emergence is one of the most exciting parts of the whole story. Chiron is not an isolated freak. It is part of a growing family of small bodies that are systematically dismantling our preconceived notions about the solar system. As we look deeper, we are finding that the weird is not the exception, it is the rule. Chariklo, discovered in 1997, was the first centaur found to have a ring system. In 2013, a stellar occultation revealed two narrow, dense rings around this 250-kilometre wide object. The discovery was a shock. It proved that rings were not the exclusive domain of planets. Chariklo's rings appear to be confined by unseen shepherd moonlets, a miniature version of the Saturnian system. Then there is Haumea, a rapidly spinning, football-shaped dwarf planet in the Kuiper belt. In 2017, an occultation revealed that it too has a ring. This ring is thought to be the debris from an ancient collision, a testament to the violent history of the outer solar system. And then there is Quaoar, another large Kuiper belt object. In 2023, occultation data showed that Quaoar has a ring located far outside its Roche limit, just like Chiron. The pattern is undeniable. Ringed small bodies are a real and apparently not uncommon class of object. So, the question is no longer, can small bodies have rings? But how many of them do? We have only observed a tiny fraction of the known centaurs and Kuiper belt objects with the precision necessary to detect rings. It is entirely possible that a significant percentage of them host these structures. This would force a radical rethinking of the early solar system. Imagine the protoplanetary disk, not just as a place where planets were forming, but as a place filled with countless smaller ringed bodies. These mini-systems would have been constantly interacting, colliding and merging. The rings of Saturn and Uranus might be the last surviving examples of a once ubiquitous phenomenon, the largest and most stable systems that survived the chaotic era of planet formation. This also blurs the lines between our categories. We have strict definitions for planets, dwarf planets, asteroids, and comets. But Chiron and its kin show that these categories are artificial. An object can be a comet, active with a coma, and have rings like a planet. An object can be an asteroid, rocky, and yet be covered in ices like a comet. Nature does not care for our filing cabinets. It creates a continuum of objects, each with its own unique history and properties. This leads to a profound and humbling thought. For years, the headlines have been dominated by interstellar objects. They are sexy, exotic, and undeniably fascinating. But what if the most scientifically valuable discoveries are not the visitors from other stars, but the long-term residents of our own system that we have simply failed to appreciate? Chiron may have formed right here, but its behaviour is as exotic as anything we could imagine. It is showing us new physics, new chemistry, and new dynamics. It is a reminder that wonder does not only lie in the distant and the unknown, it lies in the familiar, waiting to be seen with fresh eyes. If a 200-kilometre ball of ice and rock can host a complex evolving ring system that defies classical mechanics, then what else is possible? What other surprises are orbiting in the darkness, waiting for the right moment, the right observation to reveal themselves? The universe is clearly stranger, more creative, and more wonderful than we have ever imagined. Chiron is our proof, and the most exciting part is that we are only at the very beginning of this new chapter of discovery. While astronomers have been grappling with the rule-breaking physics of Chiron, a parallel revolution has been quietly unfolding in the world of artificial intelligence, a revolution that promises to transform not just what we know, but how we discover what we know. In 2025, researchers unveiled a system known as AI Newton. Its capability was as simple to state as it was profound to contemplate. It could derive fundamental physical laws from raw, noisy experimental data, without any prior knowledge of physics, without being programmed with the concepts of force, mass, or energy. This was not pattern recognition. This was not curve fitting. This was genuine concept formation and law discovery. The system was fed data on the positions and velocities of objects. From this chaos of numbers, it independently identified the concept of momentum. It discovered the principle of conservation of energy. It derived Newton's second law of motion, ephemer, and the law of universal gravitation. It did in hours what took humanity centuries. The implications of this for a field like astronomy and for a problem like Chiron are staggering. Astronomers are currently drowning in data and starving for understanding. They have the occultation-like curves, the JWST spectra, the historical brightness measurements. They have complex failing models. Now imagine feeding all of that, every data point, every pixel from every observation of Chiron spanning decades, into an AI Newton-style system. You would not ask it to test a specific model. You would simply ask it, what are the fundamental principles that govern this system? What laws explain this data? The AI might return an answer that no human would ever have considered. It might find a relationship between the phase of Chiron's tumbling rotation, the spectral signature of a specific ice, and the density of the second ring. It might derive a new stability criterion for rings around irregular bodies that incorporates not just gravity and distance, but also particle porosity, solar radiation pressure, and outgassing torque. It could propose a new Chiron law of small body dynamics. This is the future of scientific collaboration. Humans provide the curiosity, the context, and the ability to ask the deep, meaningful questions. AI provides the raw computational power, the ability to see patterns across vast, multi-dimensional parameter spaces that the human brain cannot navigate, and a freedom from the cognitive biases that often lock us into existing paradigms. Together, we can accelerate discovery in ways that were previously unimaginable. Chiron, with its defiant rings and mysterious activity, is the perfect test case for this new partnership. Its anomalies are a direct challenge to our existing laws. It is begging for a new formulation. AI Newton and its descendants might just be the partners we need to hear what it is trying to tell us. As Chiron defies the large-scale classical physics of orbital mechanics, a similarly strange revolution is happening at the opposite end of the scale, in the quantum realm of material science. In a laboratory in 2025, physicists announced a breakthrough. They had observed and controlled a quantum metric effect in a magnetic material called terbium manganese tin, TBM6SN6, at room temperature. The quantum metric is an esoteric concept, a geometric property of the wave functions of electrons in a material. It describes how these electron waves are distributed in momentum space and influences how they respond to electric and magnetic fields. Normally, observing such delicate quantum geometric effects requires conditions near absolute zero and enormous magnetic fields. But in this material, the researchers could tune the quantum metric using modest magnetic fields at everyday room temperatures. They observed this through a second harmonic electrical response, a nonlinear effect where the output signal is at twice the frequency of the input, a direct signature of the underlying quantum geometry. This is not just a laboratory curiosity. It opens the door to a new class of devices, ultra-sensitive sensors, novel memory storage, and potentially new forms of computing that operate on quantum principles at practical temperatures. The parallel to Chiron is striking. Both are systems where reality behaves in ways that classical physics says it shouldn't. Chiron's rings exist in a zone where classical tidal mechanics demands they become a moon. Electrons in this material behave according to quantum rules in a thermal environment, where classical physics says all quantum coherence should be washed out. Both are boundary-pushing phenomena that reveal our models are incomplete. They show that nature has a hidden toolkit of effects and behaviors that operate at the boundaries between regimes, between classical and quantum, between order and chaos, between stability and collapse. Studying Chiron's rings might teach us about emergent organization in gravitational systems. Studying quantum metrics in materials might teach us about emergent organization in electronic systems. The underlying mathematics of stability, resonance, and phase transitions could have deep and as yet unknown connections. It is a reminder that the quest for understanding is universal, whether the subject is a comet 3 billion kilometers away or a crystal on a lab bench. The surprises are not confined to the frontiers of space and the quantum world. They are also happening here on Earth, in places we thought we understood. In 2025, oceanographers published a startling finding in Science Advances. The deep Arctic Ocean is warming rapidly. This was not the well-documented surface warming driven by the atmosphere and melting sea ice. This was a hidden change happening in the abyssal depths, hundreds of meters below the surface. The mechanism was both unexpected and unsettling. The source of the heat was the Greenland Basin, a region between Greenland and Svalbard where cold, dense water forms and sinks, flowing along the seafloor into the Arctic Basin like an underwater river. This process, part of the global thermohaline circulation, has always been the source of the Arctic's deep, cold water. But now, that source water is warming. Climate change has altered the temperature and salinity of the surface waters in the North Atlantic, and these changes have propagated down, changing the properties of the deep water itself. Now this water, which used to be near freezing, is a degree or two warmer. When it flows into the Arctic, it brings that heat with it, warming the deep ocean from below. The implications are profound. This hidden heat could destabilize long-term climate models, which have largely focused on surface and atmospheric processes. It could accelerate the melting of sea ice from underneath, create feedback loops that alter global ocean circulation, and disrupt the fragile ecosystems of the deep sea. The parallel to Chiron is uncanny. Both systems present a calm, seemingly static exterior that hides a roiling, dynamic interior. The Arctic Ocean appears as a vast, frozen and unchanging plain, but kilometers below, a thermal engine is throbbing, reshaping the entire system from within. Chiron appears as a faint, inert speck of light, but in reality it is venting gases, crystallizing its interior and actively maintaining a complex ring system. Both are powerful reminders that what we see on the surface is often just a mask for the deep, hidden processes that truly drive a system. To understand them, we cannot just skim the surface. We must have the patience, the resources, and the technology to probe the depths. In 2024, the line between the natural and the artificial was blurred in a spectacular fashion. Researchers used a large language model called ESM3, trained on the language of protein sequences, to simulate 500 million years of evolution in a matter of weeks. The result was ESM-GFP, a fully functional green fluorescent protein. Its sequence was only 58% identical to any known natural protein. It was a genuinely new creation, evolved in silico and then synthesized into a real, physical molecule that glowed just as predicted. This is evolution as an engineering tool. It is the power of natural selection, variation, selection, amplification, harnessed and accelerated by artificial intelligence. Now draw the parallel to Chiron. Chiron's ring system is a product of natural physical evolution. Particles are launched, they orbit, they collide, they stick or they don't. Over time, through this process of physical selection, a stable structure, the ring system, emerges. It is self-organization through blind physical law. The creation of ESM-GFP is self-organization through simulated evolutionary law. Both are processes that generate complex functional structure from simple rules and random variation. One is happening in the space around a distant comet, the other on a computer cluster in a lab. This convergence points to a deeper truth about the universe. It is creative. It has a tendency to generate novelty and complexity through iterative processes. And now, we are learning to partner with that creativity. We can guide evolution to design new proteins. Could we someday guide physical evolution to engineer planetary systems? Could we simulate Chiron's ring dynamics over millions of years to see how moonlets form, and then use that knowledge to understand the birth of planets? The boundary between studying nature and collaborating with it is beginning to dissolve. Chiron shows us natural creation. AI shows us artificial creation. Together, they are showing us that creation itself is a fundamental process in the cosmos. We end our journey where all deep mysteries eventually lead to the fundamental nature of reality itself. In 2025, a team of physicists published a proof arguing that the universe cannot be a simulation. Their argument was not based on processing power, but on mathematics, specifically Gödel's incompleteness theorems. Gödel showed that in any sufficiently complex formal system, there are statements that are true but cannot be proven within the system. The physicists argued that if the universe were a simulation, a formal algorithmic system, it would be subject to these same limitations. But, they contended, physical reality contains aspects that are non-algorithmic, truths that are accessible to us, but that could not be derived from within a purely computational framework. Therefore, the universe cannot be a simulation. What does this have to do with Chiron? Everything. If the universe is not a program, then its anomalies are not glitches. They are features. Chiron's impossible rings are not a bug in the code of physics. They are a sign that our understanding of the code is incomplete. The universe is not a neat, predictable algorithmic machine. It is a complex, emergent, and genuinely creative reality, capable of producing surprises that no algorithm could necessarily foresee. Chiron is one of those surprises. It defies the simple, classical rules we thought were universal. It shows us that reality is richer, more textured, and more wonderfully strange than any simulation could ever be. Its existence is a testament to the fact that we live in a real, unfolding, and mysterious cosmos, one that is always ready to show us something new if we are only brave enough to look. The journey to understand Chiron is far from over. It is, in fact, just beginning. And as we continue to watch, to question, and to wonder, we can be sure of one thing: the universe has many more surprises in store.